Hello everyone. Right now I'm going to talk to you about how to cook planets in the lab. That's for sure. But I'll also you'll also learn how you can use these things to identify what these planets or exoplanets are made of. But first, solar system. In our solar system, there are 8 planets, 8. And the inner solar system has 4. You can see Earth here. Does it work?
Oh.
Yeah. So this is Earth here. To scale, you can see it's very tiny compared to rest of the bodies in the solar system. And the inner 4 planets constitute rocky planets, and they mostly have solid surfaces, and that's why they are called rocky. And the outer ones mostly have gas, and that's why they can be classified as gas planets. And of course, I'm interested in the rocky ones. You know why? There's some growth out there. So what are these exoplanets actually? So exoplanets are the planets orbiting stars you see in the night sky. And Thibaut told us why you cannot see them. They are very close to the star and they are faint. But with current space missions, we have been able to find a lot of these planets. And their sizes range from sub-Mercury size to planets larger than Jupiter. And their surface temperatures are, for some of them, extremely cold. And for some of them, they are so hot that rocks are molten on the surface. So let's talk about some numbers, because astrophysicists also love numbers. So there are about 200 billion stars in our galaxy alone. And in our observational universe, there are about 100 billion galaxies. So let us just say moderately there are 2 planets around every star. So can somebody tell me that makes how many exoplanets? So this is the number. So it's called 40 sextillion. I looked it up.
40 sextillion.
And out of these, we have discovered 4,000. So you might think this is a small number, but this is only in the last 3 decades. But yeah, we have still a long way to go. So how can we explore exoplanets? No, not until a few centuries. So right now, we have to use telescopes. They're really far away, so telescopes is the only way to directly observe them. So astronomers are doing this. Bern is heavily involved. Kaustubh is gonna try to understand atmospheres of these exoplanets. And then we also use computers to try and put some physical laws to test and get more information out of it. But in this talk, I'm going to talk about how you can use a microscope in a laboratory to study these exoplanets, and especially their interior structure and what minerals make up them. So what is beneath the surface of the Earth? Our planet is actually a giant onion.
So
you can put it inside a platinum capsule. So these are very tiny. You can see the diameter of these capsules is really 2 millimeters. And you insert all this sample inside the platinum capsule, and you weld it shut on both sides, and then it is ready for experiments. And then you can perform experiments in a machine like this. It has a very innovative name, high pressure, high temperature experiment. So you basically what you do, you increase the temperature to very high temperatures and pressure to very high pressures. And once the reaction takes place, you let it run for several hours, or sometimes in some cases up to several days, and then you extract the sample. You study it separately. And this is how the sample looks like. It's very small. Again, it's the same platinum capsule which I showed you, but it's cut open, so you can see the cross section of the sample. And then you can take it to a special microscope. So this is called an electron microprobe technically, but basically it's an electron microscope where you can measure different elements inside the microscope. And then you can take pictures and also analyze what's in there. So this is a boring grayscale picture from the microscope. You look at several of these, and sometimes the features are so small, it's very difficult to identify different phases. So sometimes we add false colors to it. So the actual image I'm going to show you in the next slide is that image where we added false color to a grayscale image. So this is how it looks like, and you see here the scale is pretty small. It's 10 micrometers. So you're looking at a very high zoom, you can say, and the pressure and temperature is also there on the left, top left corner. So what different colors represent here are different minerals. So after our analysis, we find, okay, this black is graphite, blue is olivine, and these red-green are iron alloys. So one is with iron carbon and one is with iron sulfur. And then, of course, these are the components of which will form the planet. If you run these experiments for, I don't know, millions of years, then you will separate these minerals in terms of their density. So the denser minerals will sink to the bottom of the planet and the lighter minerals will rise. So now let's go back to the onion. So again, how this planet's interior will look like, that's the question. So let's start from really the core of the planet. So which would be iron alloys. So the iron carbon alloy is denser than the iron sulfur, that's why iron carbon alloy goes to the center, and then it will be surrounded by the iron sulfur alloy. And then there would be olivine around it. And then the last phase, graphite would be around it. So this is what this experiment can tell us. There are different layers in the planet. But there is one interesting thing. So these experiments I ran to pressures of 40,000 atmospheric pressure. But if you go beyond 50 or 80, between 50 to 80,000 atmospheric pressure, then you actually turn graphite into diamond. So if the pressures are slightly higher, the bottom layers of the graphite, which are at higher pressure than the top layers, would turn into diamond. So essentially, this kind of structure would be there in that planet. So if you're walking on that planet, you probably are walking through a lot of dark mountains made of graphite and continents. And if you dig deeper, you might find diamonds. So that's an interesting place to live, but I don't know how you survive there. Yeah, yes, so Daniel already told you about this. So if you still are interested, you can talk to me afterwards for a while.